Okay, then I would say a few words and start the session. So we are happy to welcome Laura Tolos today for her first lecture on the subject of strangeness, strange matter and application to compact stars. And Laura is a well-known expert in this field, and she got her PhD in Barcelona, and then she had many contracts in Europe, in the Netherlands, in particular in Germany. She had a von Humboldt fellow and also an Heisenberg fellow in Frankfurt. She also had a Ramon y Cajal fellow in Spain, which is also important, and before then becoming a staff in Barcelona. So we are eager to listen to Laura. So Laura, please.
Okay, thank you. Thank you very much for the invitation. So yes, I'm going to talk about, yes, strangeness. And actually, well, there are kind of 4 lectures today, during this week and the week after. So, and I divided a bit those, I guess you have to look at the program that we had, like kind of the abstract, right? So we are actually, I'm going to start with interaction with Hybrons. So basically, to show you a couple of ways of constructing the interaction with Hybrons among nucleons, basically. And well, the ideas also apply for Hyperon, but I'm going to concentrate on Hyperon nucleons. And this is what I will talk today. Then the next one was actually supposed to be about Hyperons in matters, but this I will move it to the third one because we have these tutorials, and the tutorials are more related to the third lecture, which is about neutron stars. So therefore I will talk on Monday about neutron stars and Hyperons. And then, yeah, on the third about Hyperons in matter. So just to show you one way of introducing matter. And finally, the last one will be about mesons with strangeness. It's actually what I started working on when I started the field of strangeness. It was about mesons, not about Hyperons. So anyway, so you can, I guess, you can stop me anytime. And well, I will not control the chat, so you just have to, speak up, I guess. So I'm going now to put full screen. Let's see, and now I guess I also have to share again, or you see the full screen.
We don't see the full screen
yet. No, you don't, right? So
no.
let me remember new share, and now I have to do it again. This one. Now you see full screen?
Right. Very good.
Okay. Good.
Yes.
Great. Perfect. So yes. So as I said, this first one is going to be about, and you see my pointer, right? Okay. If not, just tell me. Okay. So I'm going to talk, as I said, interaction with Hyperon. So, and basically the next, I think it has to be so. Now it goes a bit slower. This is the outline of today's lecture of 2 hours. So basically, I'm going to introduce what Hyperons are. Probably most of you know, but for those who doesn't know, I'm going to tell you about what they are, which is variance with strangeness. And then I will, highlight the way that hyperonuclear and Hyperon interactions are built. And I will concentrate on, and present what we know, and then highlight how, from the theoretical point of view, we try to construct these interactions, okay? And then I will show you 2 ways of building those, which is the first one based on meson exchange models, which is let's say one of the first manners of ways that this was built. And we will have an example. So I also decided, to make some calculation analytic. Well, it's going to be on the screen. So anyway, you will see. And then I will say a few words. So I'm not going to derive, okay, this interaction from chiral. This is called chiral effective field theories, but just to have an idea of how these things come and how it looks like, okay? And then if we have time today, I don't know, I will talk a bit, just a few slides on hypernuclei, which is a place where we can find Hyperons. And then, well, the bibliography will be the last one. So let's start then with Hyperons in what they are and where to find them. So Hyperons, as you know, maybe some of you know, is a baryon containing one or more strange quarks, okay? So here you have a table that you can see what we call hyperons. So basically the lambdas, the sigma states, the cascades, and the omega. And this would be in the quark model, their quark composition, so up, down, and at least one strange quark for lambdas and sigmas, and then two strange quarks for cascades, and three strange quarks for omegas. Here you see, if you know a bit of group theory, so where, we usually talk, they are, lying, the lambdas and sigmas and cascades lying in the same octet as the neutrons and protons, and then we have sighted states where you have the omegas and also the deltas. So this will be the decuplet, okay? So anyways, just to show you also that this is the kind of particles I'm talking about and the masses that we are discussing, okay? So if you know or remember, what actually is written here, the mass of the nucleons, which is around 940 MeV, for lambdas, we are talking about 1,115 MeV. So that means what? Around 70, 80 MeVs larger in mass. So it's something actually interesting. Also for the appearance of the particles, particularly I will discuss later on neutron stars. So let's move first where we can find them. Well, we can find them, for example, what they are called is hypernuclei, okay? Hypernuclei, well, is the word you might guess. It means that nuclei with hyperons, okay? So basically you just substitute, one of your neutrons or protons by one of these hyperons. And then you build up this, okay? There are different ways of building these hypernuclei or, experimentally to create them. And then I will mention it as well, also a bit fast. And actually you can see here in this chart, let's say, where you see different reactions and producing, new nuclei with a strange particle. So you have, if you think about, your nuclei, the nuclei chart, okay, now you have in the zeta axis, you have the strangeness. So then you start adding, if before you had hydrogen, helium, now you have something which, a lambda, for example, that binds to helium, okay, or to lithium or beryllium, okay? So you have, let's say, a new axis, this what we call a strange axis, and the different ones are piling up depending on the strangeness number. So here you have strangeness -1, and then when you have two lambdas, you have strangeness -2. And these are the different examples of actually hypernuclei that experimentally have been created. These are the different reactions. I will mention it later. But why is interesting? Well, you have a new spectroscopy, you have new nuclei, okay? So you have a new set of, states, and then is a new field of a spectroscopy. And of course, you get information on the strong and on the weak interactions between hyperons and nucleons, right? Because first of all, you have to bind these things in nucleus. So it has to have some attraction in principle, so some interaction, but also how these hypernuclei later on decay. Then you also get information on this lambda, for example, nucleon going to a nucleon, so the weak force. Now, well, this is actually what I was mentioning. So here you see it bigger. And this is one place, okay, as I said, where you can find strangeness and actually where you can actually create it in here experiments in Earth. But of course in neutron stars, and this is more fancy if you want, or more interesting, but more. It's a scenario where you can also find strangeness, and this I will discuss actually on Monday. And just that highlight that we don't know what's going on inside neutron stars. Okay, we might know, and we think we know, like what's happening in the outer layers because of the densities we have there of these neutron stars, which are densities that we can test here. But as we go towards the interior, those densities that we are having, you can imagine this matter being compressed on those large densities, we don't know what's happening there. So we don't have a control on the physics, right? So there are different possible scenarios that we have inside the neutron star. So we might have, neutrons, protons, electrons, or we might have quark matter, okay? Or we might have mesons there, or we might have hyperons, okay? So these are different scenarios that people have been trying to model in order to understand at the end of the day the properties of these neutron stars, because it matters basically what is in the interior in order to get the properties, the masses, the radius, the cooling patterns of those objects, the evolution. So it really matters what's in the interior. And then one possibility, as I said, is having these Hybrons there. Now, again, this is an interesting scenario, because then, I mean, if you can test and you assume you have this species there, and then you calculate some macroscopic quantities, then you can get an information. I mean, comparing with observations, you might get an information on these interactions. Okay, so here there is a kind of a short summary, very short, on things we think we know. Okay, on the hypernuclear Hyperon interaction. So basically, there is, I mentioned hypernuclei, but there's also scattering data. Actually, the scattering data up to very recently was quite old. I'm talking, I mean, in the 90s. I don't know if this is old, but okay. Already the 90s are far, and even 80s. I mean, so anyway, so the point is that we have very little or scarce information on hypernucleon, and this is basically because it's difficult to have these hyperons, you know, to create this, for example, the beam fluxes with hyperons. I mean, it's very difficult because hyperons decay, the short life, okay, of these particles. We are talking, for example, of the lambda of the 10 to minus 10 seconds, okay? So because of that, there is not so much information. I mean, there is like less than 50 data points and very few events for the cascade nucleon. If you compare for information, for example, on nucleon, okay? So, but this is now I'm talking in the past, I don't know, 5 years, like being improved in the sense that we have some new techniques, okay, experimental techniques based on what is called femtoscopy. I'm not an expert, so I cannot tell you much about that, but what I can tell you is that they get some kind of correlation functions that are really connected with the so basically they they analyze what they're called correlation functions. So basically some events in the same reaction as a function of events in the different reactions. And then they out of these, they can get information on the interaction itself, okay? Regarding hypernuclei, I showed you this chart before. So there is more than around 48 lambda hypernuclei, so hypernuclei with a lambda. There is few lambda hypernuclei and also few cascade hypernuclei. And then it seems there is an evidence of one sigma hypernuclei, although this also is kind, let's say, controversial in the sense that people are talking, about repulsion in that channel, okay, in the sigma nucleon channel. So basically, if you have hypernuclei, there should be some kind of attraction, okay, otherwise it cannot bind, okay. But anyway, as you can see, and if you know a bit of nucleon, and the nuclei chart, you know that there's more information about nucleon than hyperon. Well, basically, yeah. Okay, so what are different theoretical approaches that people usually, people work on in order to build that interactions? There are, from the late 80s, models which are called meson exchange models, and this is models that I'm going to discuss now, you will see, on how to build the hyperon-nucleon and hyperon-hyperon interaction, starting from nucleon. So basically the idea here is that the mediator of the interaction is a meson, okay? So this is based on the old idea of actually Yukawa, okay, in the 30s, end of 30s, I think 35, on the idea that the, mesons can be the mediators of the interaction between two nucleons. So the idea would be to follow this and then construct hyperon-nucleon, hyperon-hyperon, imposing, of course, SU3 flavor in the sense that you imply some extra symmetry, including strangeness, okay? This is work that has been followed by the groups of Jülich, for example, and Nijmegen. So here you have some names and the dates for the references. This I will discuss now. Okay, and then, well, actually, I will show you a bit how this nucleon-nucleon meson exchange interaction is built, and then I will indicate you now what hypernuclear and hyperon, how this is done. There is also more recent way of approaching, which is this effective field theories using chiral symmetry. This is also actually part of the people already working on this mesonary change already are working on that. So this is Jülich von Munich collaboration. So basically the idea is to start from an effective theory, which mimics, you know, the physics of the QCD Lagrangian, but with different degrees of freedom. You don't have quarks, you have here baryons in this case. Okay, you might have mesons and baryons. In this case, of course, you have baryon. And I will discuss a bit later as well. But the idea, you know, is to build this interaction where you, this Lagrangian, where you implement or you mimic, as I said, the physics that is in QCD Lagrangian, and through some symmetries, assuming some symmetries. Actually, this is where the chiral word comes from. And once you build this effective theory, the nice thing of those is there is a systematicity, okay? The idea that you can build interaction and you can build different order by order, because you can set on a scale, okay? And a scale that relates the low energy scale with the high energy scale. I will mention it later, okay? So, and these are basically the people who have built these kind of interactions. And then, of course, you have other ways of approaching, like based also on quark, they are called quark model potentials. So these are again starting, those people working on this field have already a lot of experience in nucleon. And the idea would be here, you know, like the baryons are built up of these constituent quarks, and then you have the interaction between them, and then you build those interactions based on these exchanges between the quarks in the baryons in that case, okay? Then you have below K approach. This is maybe more general. It's a low momentum potential. So basically here the idea is to integrate out the high energy part, which I will mention, it means short distances is where the problem of the Pauli appears, you know, all this repulsion. And the idea is that construct in some sense some universal interactions applied for low momenta using renormalization group techniques, okay? Actually, for hypernucleon, there is not much. There's a lot of it on nucleon, but I can tell you, because hypernucleon, since we don't control much, okay, the parameters, because there's always some parameters, some couplings, because we don't have so much information on the experiments. So then it's difficult actually to build this kind of interactions. But okay, this is another way, and people have to work on that. And of course, we have lattice calculations, okay? Because you can put Hybrons in the lattice and, you know, try to solve all these correlators. And so these are actually two main groups. There's this whole QCD in Japan, and NPL-QCD, which is European, American collaboration with different approaches to the problem. And yeah, they also have tried to get, let's say, the hypernucleon, hyperon interaction. Okay, so I'm going to talk about these two. And I will start then with the meson exchange models and with the Yukawa idea, okay? Because let's start with nucleon, so you understand this Yukawa idea, and then we move on to the hypernucleon, hyperon. So for those who doesn't know, Yukawa actually was, you know, got the Nobel Prize actually for let's say theorizing or hypothesizing, making the hypothesis that pion was the mediator, okay, of the nucleon interaction, okay? So you can imagine in that time, you know, they maybe 10, 20 years before they had discovered the existence actually of the neutron, okay? Maybe even less. And now you have neutrons, you have protons, okay? Before it was thought only that we have protons and electrons when at the beginning, but then you have neutrons now, and then how you construct the interaction. And then there was QED by then. And then it turned out, you know, QED, the photon is the the mediator, okay, of the interaction. So the idea of Yukawa was, we have maybe a similar mediator that helps us to explain the nuclear-nuclear interaction. And this was the idea of this pion, as this meson, it means intermediate, okay? So mediator. So here you have, QED, and this is what I'm going to show you a bit of the analogy of the idea of Yukawa, okay? So you have QED, so you have a field of particles with zero mass, okay, which are the photons. And then you have, maybe I should go to this slide that I was a bit lazy, to be honest, to put it in LaTeX. But the idea, is that you have the Lagrangian of QED. So you have here the baryonic part, okay? Imagine these are the fermions, the nucleons, and the antinucleon, okay? So this is the kinetic term. Then you have here the electromagnetic part, okay? You have the electromagnetic strength tensor. And then you have here the interaction of these nucleons with this potential vector, okay? That has this information on the photon, okay? So this is the electromagnetic strength tensor. And the idea here is, in order, we want to get, let's say, we want to get solve the Euler Lagrangian equations in order just to get which is the equation, the motion from the photon field, okay? So the idea, as I said, is to go through the Euler Lagrange equations. So basically you take, as your field, okay, this potential field, okay? And then you do this. And then you end up here having, the field equation for the photon field, okay? So this, I guess it looks familiar. Of course, then you can work in some gauge. And here, for example, use, the gauge, the Coulomb gauge. So basically, we are considering this nu zero, this one of this component, to be temporal, the time-like. And then by doing that, you substitute here as is done here, this expression here. And then in that part here, you are just taking, of course, the gamma zero, okay? And basically now, assuming this is the source term, okay? This part here is always called the source term. So basically here, you're assuming that there is a point-like interaction. So basically you're assuming that you have like some delta, like the charge is localized, okay, in a point. And if you do that, you end up, in the static limit. So basically you're only considering that you have low energies, you end up having what is called the Laplace equation. And then you have the famous, Coulomb interaction, okay? This 1/r and the charge of the electron, okay? And this is the potential, the Coulomb potential, okay? The meson theory, so going back, so this is this part here, okay? So you end up having the Coulomb potential, okay? That all of you know. Now you go and do the same. I mean, this is Yukawa's idea, okay? But now you have something which is non-zero mass, okay? So in the non-zero limit, the Lagrangian is similar in the sense that you have now, instead of this strength field tensor, you have this field, which is the meson field. But the difference here, what you will see is this term here, the kinetic part and the mass part, okay? And this mass part is actually the one that is giving you, as you will see, the Yukawa potential. So basically, the idea is to do a similar thing. So the Euler equations, just to get the potential. This is what we want. So you do this, as I said, Euler Lagrange equation. So you get this equation here, which is actually the Klein-Gordon equations for those who have done a bit of mesons. Again, you're assuming here that all the source is concentrated in a point. And then again, in the static limit, you transfer to kind of a Laplace here, but you have this mass term here, okay? And by doing this and solving, you get a potential that now it goes 1/r, but it has an exponential that goes with the minus the mass and the distance. So basically, this is telling you the finite range of the interaction. Okay, this is as you probably know, the Yukawa potential. Okay, so the fact that you are now exchanging particles with a mass, it's reducing the size, okay, of the range of the interaction. Okay, and this is also, thinking about pions and what's the range of the nucleon-nucleon interaction. We are talking about 2 Fermis, more or less. Okay, so and this is the idea. as I say, behind the Yukawa, okay? So, and this is the idea behind the meson exchange models, okay? To mediate, in this case, I'm talking about the pions, but as you know, later on, we know that there are other characteristics of the nucleon-nucleon interaction that could not be explained with the pion exchange. And this is what I'm going to show you. So this we saw. So actually how people used to do, starting from the lowest diagrams, because basically the idea is that you have to consider that the exchange of boson among nucleons in quantum theory is considered in terms of a perturbation theory using Feynman diagrams. It's not a perturbation theory as you might think, this coupling which is small. It is in terms of that the diagrams that has the less number of that has the exchanges, the number of exchanges is less, is the ones that dominate. Okay, so the ones that have one meson exchange will dominate over others that have two meson exchange and some more complicated ones. Okay, so that's why we start here. And so at the lowest order, I mean, it will be these Feynman diagrams. I hope that you know a bit of Feynman diagrams, but if not, I'm just telling you how these things are computed. So basically the idea is that a nucleon in this case, okay, interacts with another nucleon, okay, but they interact through this exchange of this meson, okay? So this is this dashed line, and they end up, with a different momentum of both of them, okay? This is the idea of this diagram. So two nucleons interacting and leaving, okay? So these kind of diagrams, the Feynman, the Feynman laws are basically, you compute this vertex here, you compute this vertex here, you compute the propagator, and then you get the amplitude, okay? So basically is what you've seen here. This is the first vertex, this one here. This is the second one here. And then this thing here is the propagator, okay? This is the structure of a propagator, something that propagates with an energy, okay? Those gammas are this vertex, the structure, okay? And this depends on the interaction, depending on the meson you exchange, okay? You will see some examples, depending on whether, well, I will show you later. And these U's, okay, are the Dirac spinors, okay? Because those are fermions, so they have some structure, some spinor, and you see here that this is the usual, way of expressing them. Okay, so you have some energy plus the mass divided by 2 times the mass. Then you have here the Pauli matrices, okay? And this chi s here is what is called the 2-component Pauli spinor, okay? So these actually are they have vectors of 4 components, okay? That in the limit where the energy is the mass, so basically this is the low energy limit, so non-relativistic. So you can even approximate up to, you end up with this expression here, okay? Now, why I'm doing that? Because I want to show you which kind of particles, they were thought to be exchanged, and in order to build these meson exchange models, okay? So basically, you start, sorry, yes?
Yeah, I just have a question, if it's possible.
Yeah, sure, go ahead.
How do you know that the diagram with more meson exchange or less important?
By doing it, okay? So, so yes, it's not, we don't have a parameter. So basically, you just start with these, and then you see that the larger ones are less contributed, are modifying, but this is not so important, okay? Not so important. They are important for some characteristics, but they are subdominant, okay? This is just by doing it, okay? So yeah, it's not like if you know effective theories, I will mention, it's not that you have a parameter of expansion, okay? And this is a problem. Okay, I go ahead, yeah? So then, if you look at the particle data booklet, so I guess all of you know this. I took this slide, is an old slide, actually from the 2004. But anyway, things in the sector hasn't changed much, so hopefully. So basically you have here all the unflavored mesons. So this is the pion, okay, pi plus, pi minus, pi 0. This is the one that Yukawa thought of, okay? But then you also have, as you increase in mass, so you might have etas, you might have sigmas. Sigmas is a story, a separate story, whether, you know, they really exist or not, or there's an issue here, okay? In the sense that it might be two pions correlated, or whether there's a sigma mass, because actually, you know, you can see here the mass and the width are, you know, similar. So this is actually experimentally some difficulty here, okay? And there are also, if you go up to 1 GeV, so 1,000 MeVs, you have rhos and you have omegas, okay? So what is the difference between all of them? Well, actually, you can see here now the different quantum numbers, okay? So basically, you have the isospin, okay, of those particles. This is the G parity. I'm not talking about that. So for me, right now, the important things are the isospin, the spin of the particle, and the parity of the particle, okay? So this is what it means, these ones. So, and basically, I'm concentrated on the spin of the particle and the parity, because the usual classification is that those, you know, that have spin equals 0 are scalars. But if you have negative parity, it's called pseudoscalar, okay? While you can see here those that have positive parity, sorry, this is pseudoscalars, the eta and the pions. The isospin is the one that is telling me actually that we have 3, like this is a triplet of particles. Well, the eta is only 1, okay? But I'm not concentrated on that part. Whether for scalars, I mean, so the scalars, you can see here that the parity is different actually, and the parity is plus, okay? So this is the scalar, okay? And then you have vectors, which the difference between the scalars is the spin again. So now instead of having spin 0, you have spin 1, and the parity is negative, okay? There is also the axial ones, which are around 1 GeV. That's why I'm not showing them here, which have plus parity, okay? But these are the first one that people, when building the nucleon, thought of, because they were being discovered at the same time, okay? You know, Yukawa said, okay, there is this pion, and then this pion is discovered in cosmic rays and in the laboratory in Brookhaven National Lab. Okay, great. Now with this pion, we try to see by doing this diagram. I'm going to show you the calculation actually, whether you can get the nucleon properties. And then you see that not all of them can be described. So then what's happening? Okay, we might have the interaction mediated by other particles, maybe heavier, we don't know. And then, you know, experiments start finding those particles, start finding those rho, those omega. And then people just say, okay, then maybe those, you know, will help us to understand better the nucleon interaction. And this is how, you know, in the beginning of the mid of the 20th century, people begin to build those models, okay? So I will show you actually how the nucleon interaction with the mediation actually of 4 particles, 3, 4, you can describe almost everything, okay, of the nucleon without being too, let's say, precise, because there are some measurements that could be better explained with exchanges of higher exchanges, okay? But with these 4, it's amazing. I mean, for me, I think this is really amazing. So how do you do this? How do you compute this? Well, as I said, you have to compute this for Feynman diagram, and here you have the rules, okay? So basically, you have to build a Lagrangian, which is Lorentz scalar and Hermitian, to conserve probabilities, okay? So this is the kind of shape that you have. So you have a coupling, which will be determined by experiments. This is a coupling we don't know. And here you have your vertex, which is given by the symmetry, depending on what are the characteristics of this meson. And then the 2 fields, so the 2 nucleons, okay? And then, well, the story here is, as I show you, so you have to compute this vertex here, I mean, to get it. So it's basically E times the Lagrangian strip of the fields. This is the Feynman rule. And the potential, which is at the end of the day, I don't want to get, which is the contribution to the nucleon potential, is I times the amplitude I showed you before, okay? So let's do an example, okay? Let's do the pseudoscalar interaction, the pion interaction, what Yukawa, you know, hypothesized, okay? So this is actually the 1 pion exchange for the nucleon, okay? So This is the Lagrangian, okay? Actually, I'm just telling you that there is a coupling, as I show you. Then there is this structure, this gamma phi, because of this parity, actually, of this pseudoscalar being interact. So this is the field. Also, I told you about the pion, and I told you that it has 3 components, like pi plus, pi minus, and pi zero. This is the isospin, okay? So there is also then appearing what is called a isospin vector, okay? So it's an isovector, that's what we call. And the idea, of course, is as I said, and I will show you in detail, to get the vertex. So basically extract first, the first idea is from my Lagrangian, I extract the interaction. I mean, this is, for example, going back, this is this one here, okay? So I have my nucleon, my meson coming here, and a nucleon leaving, okay? So I want to get this structure here. I want to get that. But first I have to get this gamma 1, okay? So going back again, and this is this gamma here for that case, okay? Because we said is I times, you can see, I times the Lagrangian strip off the fields. So basically I times the Lagrangian is I times I is -1, and this -1 makes a plus here, okay? So this is the structure, okay, of this vertex. And then you compute this, okay? For one vertex and for the other one. And this is what I'm showing you now, okay, in more detail so that you know. So here it is, okay? So again, I was a bit lazy. So basically, I want the 1 pion exchange, okay? So what I'm telling you is that I said the potential is I times the amplitude. And the amplitude is what I show you here, okay? This is one vertex, you have the spinors, the Dirac spinors. Then you have the other vertex, okay? And then you have the propagation, okay? This is the propagation of the pion, okay? Good, the vertex. This is what we did before. Minus coming from the Lagrangian that is not here, okay? This minus here. If you don't understand something, stop me, okay? If you don't see some step, okay? So is, as I said, minus, and then this I from the Lagrangian, sorry, again, I may be here, I of the Lagrangian, this minus, okay? And then I times, so you put another I. So you end up having this G pi NN gamma phi tau, okay? This is that one here, okay? That's okay. Now I'm computing the vertex. Okay, so for the vertex, I have to know a bit of gamma matrices, okay? Because as I said, there's a gamma phi, and this is related with this parity, okay? So you have to compute this. So I put it here, G pi NN. This is the coupling, okay? This is the coupling of pions with nucleons. Actually, it's related to the decay. This is the coupling. Then you have, again, I'm not putting anything, but doing the writing here. This one times this vertex gamma, it has a gamma 5, this gamma 5 here. Then the U is here, okay? So this is the incoming and this is the outgoing, okay? Yes, okay? The incoming nucleon and the outgoing nucleon, okay? And this is the tau. The tau for that first vertex, okay? This is this tau, okay, for the first vertex. So then actually, if you have ever worked on spinors and gammas, you see that actually this is multiplying matrices. So basically, you do, oh, I forgot an n here and an n here. It's J pi NN, and then U bar, it means the U plus, so the, what is this called? The, and I have forgot the name, is the complex conjugate, okay? So the conjugate, so basically you have U, the transposed, sorry, the transposed. So basically U plus gamma 0, okay, this is what it means, U bar, okay? And then gamma 5, U times tau 1, okay, that's it. And then you do the multiplication. I mean, this U, in this, you can do anything. You could go gamma 0, gamma 5, or you could do gamma 0, this one. So sorry, first I show what is the U plus. So this, so it's putting, instead of having, you know, a vertical, a vector, you have the, you know, like a raw vector. So you have here, what is indicated here, this Pauli spinner, okay, with the plus, and the sigma 1 p1 prime divided by 2m sigma plus, okay, for the the Pauli spinner. So what I have done here is just putting this, doing this, okay, just put it in the, so if you look back here, sorry, if you look back here, it's just doing this, but in line, okay, in a row, okay. And then you have gamma 0, gamma 5, and then the rest, I mean, this is the vector, the U, the Dirac spinner, and then the tau. Now what I do here is what I try to show you here. Put gamma 0 and do the multiplication gamma 0 with the U plus. So basically I'm doing gamma 0 and this, so G pion nucleon. And then by doing the gamma 0, you have here what it is the unit, is this matrix, which is 1 and in the two first components and -1 in the two second ones. Okay, so and because of this -1, you get this minus sign here. And then gamma 5 and the same, okay, the vector and tau 1. Now I do what? I decided to do gamma 5 with that one, okay, with that term here. So basically I decided to do U plus gamma 0, gamma 5. So you do this, and gamma 5, you have to remember that is 0, 0 in the diagonal and 1 in the other one, not in the diagonal. And then you get this term actually crossed here, okay? And then the other one here. And then you have, again, this is not being changed. So this is the same, this part here. And of course, now you use that, you know, the Dirac spinners, the multiplication of the Daga one with the non-Daga is equal 1. So then you get up, you know, the constant, and then you get this term here, because this is this one times plus this one, this times this one, and tau 1, okay? So you can see here already that I'm getting to an expression, which if I express in terms of the transfer momenta, which is the difference between the outgoing and the incoming nucleon, it will look like this one here, sorry, this expression here. So it will be the coupling times minus sigma, the Pauli matrix in that vertex, times this momenta divided by 2m, and the isospin structure, this vector tau. You do the same for the other vertex, and actually there is only a difference, and the difference is because the momenta, okay? Because the momenta is defined, you know, this is incoming momenta, so it's the difference between p prime 1 and p1 2, but then the other one is p2 minus p2 prime, okay? So there is the difference in the sign, but this term on this term, because the vertex is actually the same and independent on and for those cases, okay? And then you go and do the potential. So you do I times this, you know, product here. So you have this term, which comes from here, the second one from here, this G squared, and then you have the propagator. And then you start, and then you try not to make any mistake, multiplying i's, okay, I times I, the minus gives you a plus, G pi squared, and then sigma, you end up with the sigma q divided by 2m, the propagator without the I, the second term, and the product tau 1, tau 2. And you arrange things and doing the static limit. We're always doing low energy, okay? I'm doing the non-relativistic limit for the Dirac spinors. I'm doing the static limit also, I mean, not low energies, basically. So I'm ending not with the 4 momenta, but with the vector, okay? With the 3 momenta. So, and then you get, because of this minus, you get a minus in front. So you get up this coupling divided by 2 times the mass squared. And then the product of the sigma 1 and sigma q divided by squared mass squared tau 1, tau 2. Okay. Did you follow more or less? Yes? Okay, I hope so. So anyways, this one here, okay? What I want to get to the point is that this relation I can express in terms of in these terms of this expression, basically using what is called a tensor operator. This is already just to indicate that there's going to be a tensor dependent, okay, coming in the nucleon-nucleon interaction coming from the exchange of the pion, okay? This is something already seen. I mean, this tensor part is the one that is telling us, for example, that that the deuteron, okay, it doesn't have a spherical shape. Okay, there is some tensor contribution. Okay, so defining this, you end up having this pion interaction. The contribution of the pion to the nucleon-nucleon interaction is given by this expression here. So you have a central part and then this tensor part. This actual expression, you can also do it. I use, how to build this Lagrangian. Okay, this Lagrangian was built by this gamma 5 interacting, okay, with these fields here. But there is also based actually on suggested by chiral symmetry that I will mention later. There is also what is called pseudoscaler vector or gradient coupling, basically where you have derivatives. Okay, and therefore, if you have a derivative here with this mu, you end up having a gamma mu's. Okay, so this is called the pseudo vector of gradient coupling, and this actually gives you the same potential at the end. Okay, of course, the structure of the vertex is a bit different, but if you do the mathematics with the gammas, you end up at the same point. Okay, okay, so this is for the pion. This is actually already I was telling you it has some tensor contribution. Okay, that is you see in the nucleon-nucleon. But there are also, as I mentioned, mesons, in the PDG, and there are different ways, I mean, there are the ways of building this Lagrangian. So this is the scalar Lagrangian, this is the vector one, and this is the tensor contribution, okay? I put here, for example, omega and rho, and I told you both of them are vectors, okay? But there is the coupling to the nucleon-nucleon can have some what is called vector contribution because it has this mu, gamma mu, and those are fields with they are vectors, so you have an extra index here, and of course you can also have these tensor structures. Okay, why I'm telling you that, because at the end of the day, this is the contribution of each of the particles to the nucleon-nucleon interaction. So the pion is giving you some central contribution that, as you can see, the mass of the pion is around 140. So it's a long range part because the mass is small. So it really describes the nucleon-nucleon at large, at large energies. Okay. Whether there is also contribution, as I said, of this tensor part that is telling me, there is not that if you have nucleon-nucleon interaction, you also have non-spherical shapes. Okay, like in the deuteron. Then there is the contribution of the other ones. Actually, if you do the same that we have done using the Lagrangian in this slide, you end up having the contribution of the sigmas and the omegas and the rho. And actually, you see here that you have an attraction coming from the sigma, this minus, and then you have what is called the spins, orbit spin. Okay. A contribution. This is also telling us that the interaction depends also on the spin of the particles. Okay, so there is also a contribution not central. Okay, doesn't depend only on the distance between the two nucleons, but also on other features, which is the spin. And the omega gives you actually the the same contribution for the spin force, the orbital and spin, with a different value. So it's, let's say it's more attractive, but there is this repulsion here, okay? And the difference here, of course, is the mass, because the sigma mass is 600. This is almost 800. So you can imagine that the energy range that is this describing from the nucleon-nucleon is different than that one. And the rho, which is similar to the omega, gives you a contribution again of the short range, but is opposite, okay? So the short range tensor force, so the short range because of the mass, the tensor force is, you can see here, and is opposite to the pion in the sense that before it was minus and this is plus. With all of that, what happens? So with this interaction, you can describe, sorry, yes, go ahead.
I have a question for the slide before.
Yes.
I don't understand why for the rho meson there are also in the
some extra
potential the two vector. I true it's come from the fact that the pion are triplets, but that's not true, I think, for the rho one.
Sorry, again, the difference between the rho and the pion, this is your question or
No,
what?
I don't understand why in the potential for the rho there are the two vector.
Two vector. You mean these
two,
ones here?
yeah,
Because
one.
of the, okay, because of the isospin. This is isospin, okay?
Okay.
The spin of the rho is 1, okay? And the pion is also 1, okay? So this is here, this is, when you have I mean, these are isospin vectors, okay? So then that's the reason why you have tau 1, tau 2, and also you have here tau 1, tau 2, okay? Because these are vectors in the isospin space, okay? And there's vectors in their spin space, let's say, okay? So this is a 0, okay? So this is a pseudoscalar for the spin, but this is a vector in the spin, okay? And then the couplings, let's see here. For example, this is the scalar, okay? So this is the scalar, so there's no gamma 5. So you see here, there is the different coupling as, for example, a vector coupling. So this gamma mu's, okay? But as the reason for the tau 1, tau 2 is because this is an isovector and is also an isobector, okay?
Okay.
Laura, the sign of the spin orbit is not visible in the slide because it is covered.
In this slide, you mean that one?
Yes, it's not visible, the sign of the spin orbit interaction.
Yes, okay, I mean, they are, this minus, this one, sorry, is plus strong, yeah, it's, okay, yeah, okay.
I would like to add a
Yes.
comment to the previous
sure.
question.
Sure.
When you exchange pions, you can exchange also charge, because the pion exists in different states. The same for the rho. And this is why come out exactly as Laura said, this structure, that lives in the space of the isospin. So that takes into account different states of charge.
Exactly.
Okay.
Exactly.
I also have a question. If you could go back to the previous slide.
That one?
Yes.
Yes.
It looks like the Lagrangian for the looks like the tensor Lagrangian used for the rho is an isovector. Is that correct?
I
mean, you have this tau vector contribution
this tau
here.
Yes.
Right? So is the Lagrangian an isovector valued quantity?
The Lagrangian and isovector quantity. No, it's coupled to these vectors here. Okay, so this is scalar. This is scalar.
I see.
Okay, because this is that's the reason why you have this tau here, because these are vectors in the space, okay, of isospin. Okay.
Yeah, I suppose I just assumed that vector notation on the phi there was actually referring to the Lorentz index. I didn't realize that that was separate.
Exactly,
okay,
it's separate. Sorry, yes, it's separate. This goes with the Lorentz. It goes here, okay, and this is where the isos and the spin space. Yes. Yes.
Right. Okay. Thanks.
Laura.
Yes.
But you showed the rho coupled as a tensor, but you could consider the rho coupled
as a vector
with an isospin vector. Current,
yes.
Right?
Yeah, this is because we know the contribution. I mean, it's stronger, the tensor part coming from the rho than for the omega, okay? Because both of them are vectors, okay? So I'm just showing a coupling, vector coupling, assuming that the omega is the dominant one and the rho are dominant for the tensor, okay?
So for you, effectively, to have the
So yeah,
I'm thinking about the Valechka model in which you couple. I mean, to consider the isospin part, you couple to the rho with the vector isospin current.
Yes, but this is because the rho has an isospin, the omega is not.
Yes, just to have that channel that is open.
Yes. Yeah, I mean, the rho is an isovector, so then you have the isospin dependence there in the sigma omega model, in the Valechka.
Yes.
Okay.
But here, instead, in your calculation, that coupling is not really important, right?
The coupling, you mean?
The coupling that you consider in the Valechka model.
I don't know if I understand your question. I mean, you mean
what I mean when you do your calculation?
Yes,
you consider the coupling to the rho as in the Vallecca model.
Okay, you mean that. Well, here we assume that the rho is a tensor. Okay, so it contributes as a tensor. Okay, then I understand. Yeah. Okay.
No, just
yes. Okay.
match the two things.
Yes. Now I understand your question. I mean, this is because, well, it's not that I know, it's that they know when they build this thing, okay? So basically the contribution, in order to express basically this short range part, okay? Because the rho and the omega are here, okay? And then they have this contribution, this vector and tensor contribution, okay?
Yes, very good.
So basically, I'm just telling you, nucleon. So this is the central part, okay? So you have this, depending on the mass, you can describe, longer distance, longer distance, small energy, okay? This is what I meant before I said it wrong. So small mass, small energy, long distance, okay? So this is what the pion describes, like 2 Fermi even larger, okay? It's short, it's finite, okay? The interaction is a finite range, as Yukawa said, okay? But still, we're talking about this region. Then the sigma, as you increase the mass, you start moving towards the center. This is the distance between two nucleons, okay? Or the relative distance between two of them. So, and then you have the sigma field, which is larger in mass. And then you have the sigma and rho. Sorry, I said sigma and rho, omega and rho, okay, which describes the short part of the central force. This is the central part, but of course, I mean, I didn't say much about nucleon. I just said that you have some tensor component and some spin orbit component, okay? And this is also important, I mean, achieved, because we know that the characteristics are there, because we know, as I said, there are spherical, the deuteron non-spherical, there is some spin orbit dependence on when you make scattering of nucleons that depends on on the momentum between them and the spin of them, okay? And this is actually described, the spin orbit, by the omega and sigma, while for the tensor part by the rho and pion. Sorry. And then, I mean, this is for me amazing. I don't know for you, but like really doing this Feynman diagram, like you change 4 things, like 4 mesons, you get the nucleon force, the features of the nucleon force, okay, nucleon interaction. So this is the one boson exchange potential. So basically you have the contribution of all possible mesons. So we have discussed pion, sigma, rhos, and omega. But you could also think about, getting up to 1 GeV. 1 GeV, why? Because then you're getting into the structure of the nucleons, okay? You're getting at energies describing the quark structure, okay? So they're already, you're entering in here, okay? So then if you think about etas that I didn't mention, it's a pseudoscalar with isospin 0. So it will be the same as the pion, because it's a pseudoscalar, only that you don't have this tau1, tau2 factor, okay? Because it doesn't have, in the isospin space is not. Or you have the A0, which is a scalar with isospin 1. So it will be like the scalar of sigma, but except that it carries this isospin product, okay, of operators. And as I said, I mean, the idea is that once you start, trying to describe, especially the short range here, okay, you enter into the structure of these hadrons, and then you start implementing, these 4 factors in order, to control this short range part, which is actually not so well controlled, okay, because we don't have data. I mean, scattering data is around up to 300, 400 MeV, okay. In this region is not controlled, okay, it's not there. We are in the region around here, okay. So what do you do with this potential? Well, this potential, the idea, I don't know, I'm already at already 1 hour. I will stop right after here, okay. So basically you try to solve the scattering process, okay, of 2 nucleons that interact, and then the idea is to solve what is called the Lipmanche finger, because it takes into account all ladder interactions, okay, all the virtual, possibilities, scattering between 2 particles, and then you can compute things like binding energies, I mean, this is one possibility, but for the scattering, you could compute, for example, what is called effective range or the scattering length. Okay, so basically, the scattering length is like in a hard spheres is like the impact parameter. Okay, and just to show you how theory matches, experiment. Okay, in the sense that you have pretty good results. Okay, with these meson exchange models. Okay, I think I will stop here because now I will give you some slides. Stop sharing. One slide on Hyperon, nucleon, and Hyperon. And on that, meson exchange, and then I talk to effective theories. Okay, so I think maybe we can stop for 10 minutes. Sorry, I was late. I didn't watch my clock.
It's okay. It's perfect. Thank you.
Okay, so
very instructive, very clear. I don't know if there are additional questions. Questions have been already asked, so and the lecture was clear. But if there are more,
sure.
Ignazio, you want to ask something? Okay, so let's stop for a while and.
Okay.
I have a question.
There's a question.
The fact that the eta is really similar to the pion except for the tau1 dot tau2 term means that the Lagrangian associated to the eta has not that piece S12, which is the tensor term you introduced previously.
No, it will be more like I mean, as you said, the A0 is like the sigma, but with a tau term. So basically it will be something like this one, but with a tau, okay? Vector here, okay? Because it's a scalar, but with a contribution. On the other hand, the other one, let's see, the eta, which is a pseudoscalar, so it will be like the pion, but without the tau. So it will be something like this one, but you don't have this tau here, okay? So you will have this gamma 5 because it's pseudoscalar. Okay?
Okay, thank you very much.
Okay.
Sorry, can I make a question?
Sure. You can.
Maybe it's more. Maybe it's more a question for the next lecture. Was just because I know when we deal with neutron stars, we usually, in relativistic mean field theories, we usually include only the sigma, omega, and rho.
Yes.
Why don't we include the pion?
Good question. Wait, I'm thinking. I'm thinking. I don't know. I don't know now. Maybe I'm. Wait. Sigma, rho, pion, change, sigma.
Maybe the range.
Yeah, I'm thinking only that the range.
The density probably, which is so high that.
Yeah.
But you have in mind, for instance, the Valechka model. I don't know.
Well, the Valechka is the sigma omega model.
Yes, but because it's solved usually at the mean field level, so if you don't have
yeah. The pion fields, yes, the average is 0. Yeah. Then I share again. You share full screen. Okay, so you see it?
Yes.
Okay, perfect. Okay, so I talk about nucleon just to show you what, starting from the Yukawa idea, how these nucleon interactions are built based on meson exchange models, okay? So the people working on Hybrons, so then, of course, they were, scientists already working on nucleon. So basically the idea is to use the same ideas, but now with including this strange degree of freedom, okay? So basically, in a few words, it would be to do similar exchanges, but of course, having into account that strangeness has to be conserved as well, okay? That has to be taken into account. Sorry, I thought somebody said something. So basically, the idea would be to start from nucleon and impose SU3 flavors. So the idea is just now we have to use our full octet, okay, of baryons. You start with a ground state of baryons. So you not only nucleons, but as I show you, you have lambdas, you have sigmas, and then you have to study the interaction among themselves. So there are two big groups working, or I think they're still working, but now it's more fancy chiral effective theories. So there is a group of Nijmegen in, well, this is in the name of a city in Netherlands, and then Jülich in Germany. And these are, of course, the people really more pushing for these meson exchange models with Hybrons. And well, all of them are starting base is the nucleon, the one that they had. So basically, there are a bit differences. I mean, I told you that, with 4 mesons, you can describe the interaction. But of course, if you want to have a refined description, then you have to go to higher order diagrams. And, there are also some fine tuning of some of the terms. And then is different in both of them. So let's say for the scattering part, all of them describe very well the scattering data. The thing always, sorry, the difference always is in this short range part, okay, which we don't have data and we don't have control. But anyway, so the Nijmegen one, as you can imagine, it's based on their Nijmegen nucleon. They can build it in different spaces in the sense that it could be done in momentum with momentum dependent interaction, or in the R configuration means R space. It includes these interactions, pseudoscalars, as I was mentioning, the pion includes vectors, the rho omega, and also scalars like the sigma. So, and then in order to go and put the strangeness, they implement this symmetry, this flavor symmetry, which means, extending not only to nucleons, but to hyperons, okay, to the full octet. And of course, as I said, to take into account the short range part, when you enter into the quark structure, let's say, we use some forms for the Gaussian, okay, form factors with a Gaussian shape. The one I think before, okay, this is not a Gaussian, okay, so this is it's more like dipole for polar terms, which is the ones that in Jülich they are used, okay, so there is some cutoff, some quantity that is fixed ad hoc in order to fit better the experiments, okay. So, and the Jülich is based on their nucleon. It's full energy dependent on localities. Well, there are some technicalities if you want. They have a scalar vector and pseudoscalars, but they also have high order terms that I was telling you, they are subdominants, but you still have, they are called box diagrams, where they have this change of 2 mesons in a different configurations. And here is that they use SU-seq. The SU-seq means that it includes the spin, okay? So they also take into account not only the flavor part, but also the spin part, and then they assume some symmetries. And as I said, the form factors to take into account this short part, the short range part, is of dipolar form in this, like similar to those ones, okay? So these are just characteristics, okay? So I'm not showing you how to compute. I mean, this is the same idea, okay, as a nucleon, only that sometimes you might have mesons that contain strangeness, because maybe you have some vertex that the strangeness is exchanged between the legs, okay? So, but just as an example to show you the scattering data coming from one of these meson exchange models, this is the Jülich 2004. And the authors are Johann Heidenbauer and Ulf Meissner. And the idea here is that to show you some scattering results. So basically some cross sections. Here I'm just showing cross sections as an example, okay? Of the states lambda proton going to lambda proton, sigma minus proton going to lambda neutron, sigma minus proton going to sigma 0 neutrons, and other ones here, okay? So, and then you have to look first to the blue line, okay? This is the theory, the model, okay? And I'm looking now at sigma minus proton going to lambda nucleon. And this will be the prediction of the Jülich model. So this is cross sections. The cross sections are related to the scattering amplitudes by some phase space and the scattering amplitude squared, okay? So, and the scattering amplitude is what I was telling you, solving this Lipmanche, which is depicted here, okay? This is a Hyperon and this is a nucleon. This is why I put the different lines. And going to, you know, the potential. So this is this green point indicates the potential that is coming from the exchange model. This is this V here. Okay, this term corresponds to that one. And then you have this diagram here, which is this B. This is here. And then you have this T, which is here. And then the propagator, which is the propagator of two particles, two baryons. And the idea is that you have an infinite series here. Okay, this is the same plot here. Okay, I was showing you that you have to solve the scattering matrix. Okay. And because this scattering matrix is related to the cross section, and this is what you can compare with experiments. You can see here, for example, the error bars. Okay, so the error bars are pretty high. I mean, this value is 175, and the error bars are like 100 almost. Yep. So the error bars. The problem here is the quality of the data. Okay, so this data is older, of course, than the model. So, but okay, the problem in all these analyses is how good the data is, because we have coupling constants. Okay, in those Lagrangians, I was showing this coupling constant. Okay, so we always need some data from experiments. Okay, so and here you can see, for example, in that sector, the data was not so good. This is what I mentioned, that recently people have started moving into this Spectroscopy. This is a technique already using heavy ion collisions. Maybe, you know, some experts in the audience on heavy ion collisions more than me than on Spectroscopy. What I know is they try to compute, you know, the events, the events in the same reaction with a certain relative momenta as compared to those who they are called uncorrelated or in different reactions. And basically this correlation factor, which is plotted here, depends on the source, on the shape and the size of the source, and it depends on the wave function of the nucleon baryons, on the baryon system. And in particular, you know, these would be the results. Okay, for this case, this is proton sigma 0 and also antiproton sigma bar 0. Okay, and the model, for example, well, here a model which is Meson exchange will be these two ones here. Okay, this is different from this blue one. This is Jülich. Those are from Nijmegen. So the older one is that one, is 97, is 1997, the version F. And this is Nijmegen soft core. Okay, this is one model Meson exchange. And the other one is more modern, on 2016. And let's say, how do you compare? Well, with these interactions, theory, you can compute scattering amplitudes. I'm sorry, you can compute the scattering amplitudes. With that, you can compute scattering length, effective ranges. So it turned out that this correlation function, it's directly connected with this effective range and a scattering length. So with the theory, you can actually do the calculations. Okay. This band, I guess, it's just because of the couplings that you can a bit, you know, change a bit in order to get a band of results. And so you see the prediction of the model and where the data, new data from Spectroscopy is appearing. Okay, is a new data because you get, in the sense that, you know, it's giving more precision. Now you have data, you know, below 100. All this information, for example, this is sigma 0 proton. Actually, I don't have it here, but the data here, I'm showing it from 100, okay? And also, it's a different variable, okay? So maybe you cannot directly compare. Sorry, you cannot directly compare. So I'm just, forget about what I said, just remember that you have a new way of getting new data and more precise than the previous one. Okay, this is for Meson exchange models. But more recently, okay, in the end of last century, well, that sounds good, and beginning of this one, you know, people already, you know, start thinking about effective theories. And this is maybe when, nuclear physicists discovered, well, first nuclear physicists discovered that we don't have mesons and baryons, we have quarks. And then we start now discovering as well effective theories, okay? What is an effective theory? So from now on, I'm going to have few slides. I'm going to give you some ideas, okay, on effective theories and some theorems and things that you will probably see in the literature. I'm not, let's say, developing much, okay? So you probably have to believe on some of the things that I say. But because my idea was that you get to the point to see how the hyperon-nucleon interaction, okay, and the hyperon-hyperon looks like in effective theories, okay, and what's the difference between the meson exchange models. Okay, so let's start with a few general ideas. So I put a lot of, ideas here in written. So, okay, QCD, is the interaction between quarks is at short distances is weak. So this is the part where we have this asymptotic freedom, okay? But as you go to longer distances, so that means long distance, small energies, you have the confinement phenomena, okay? And this is seen in this famous running coupling constant, okay? That for low energies, you have this coupling constant which becomes larger, where in these higher energies, the coupling constant is smaller, and therefore, actually, you can work in perturbative theory. Now here we're talking in perturbation theory as, like a possibility of doing an expansion using a small scale, okay? So the effective theories were born in the idea of dealing with this non-perturbative regime. But of course, the idea is that the dynamics in this low energy region does not depend on what is happening on the high energy region. The idea was also to have a systematic approach. This is what I have here, where your effective theory retains certain physical, certain dynamics that is governed at this energy range. So it matters what's happening at low energies. I don't care if there's multiple scatterings or whatever at high energies, okay? I don't care between quotation marks, okay? Because somehow you will also have information in the couplings, okay? And the idea, of course, is to avoid models, so it's not a model. And of course, in order to establish this effective theory, you need, and in order to do actually have systematicity, a way of adding higher order corrections, you need a small parameter, okay? And this is obtained by constructing a fraction between two physical scales. So basically that are really separated. For example, in here, I'm showing you have the light quarks, okay, which the masses are very small as compared, for example, to the charm one, which is above this 1 GeV. So basically, if you're dealing in that region here, so you can set up that, the parameter, for example, is your pion mass, because we also deal, now I will mention, on small energies with respect to a larger scale, okay, which is of the order of 1 GeV in this case. So the idea is to find a small parameter that you can have an expansion with. And of course, the interaction now is not between quarks. So you have an effective theory that is not between the quarks, but it retains the dynamics of the QCD Lagrangian. Is between hadrons at low energies. So therefore you need, another degrees of freedom, which are the mesons and baryons. And as I was saying, you have the physics of the QCD Lagrangian has to be retained. So you have to mimic, the effective Lagrangian through a set of operators and associated constants. I'm just, as you can see, I'm just blah, blah, blah a lot, but just that you have the concept, okay, the idea. So you have a set of operators that somehow retain the dynamics of the QCD Lagrangian at this low energy, okay? The symmetries actually of this Lagrangian at low energy, and just coupling constants, you would know them, you could create this effective theory if you knew the field, if you could knew, comparing with the complete theory. But since it's difficult to the exact solution, then you basically, these constants are determined by experimental data, okay? So it's like, you have your Lagrangian of QCD, you want to solve in the non-perturbative regime, so low energies, so you have the problem, okay, of not being able to solve, okay, the QCD, with the QCD Lagrangian. And then you build up an effective theory that tries to mimic the physics of the low energy of this QCD Lagrangian with different degrees of freedom. We are not having quarks, we are having mesons and baryons. And the power of this effective theory, if you're able to build that, is that it will contain, as I said, the dynamics, the symmetries of the fundamental theory. So it has 4 pillars, the symmetries, that contains the symmetries. You could have a power counting because you could define a small parameter. Okay, so you could have a power counting in terms of that small parameter. So you can add order by order calculations. And if you can do that, you can estimate corrections because you at each order. So if you compare, you do what is called the leading order, and then you compute the next to leading order, then you can estimate, my difference between the next to leading order and the leading order, and then estimate your corrections, what you're missing, okay? And of course, the idea as well is it's based that it's systematic, it's not a model, okay? So it tries, as I said, to have some symmetries, to build up, to have an expansion in terms of a small parameter, and to allow with this parameter to have this power counting in order to add order by order in a systematic way, and in this way to estimate corrections, okay? So if you will like, as an algorithm, I took it actually from Asum, who is an expert on effective field theories, Asum Parreño of the University of Barcelona. So the algorithm, in order to build the effective theory, will be first determine what are your soft and hard scales of the system, okay? And what are the degrees of freedom, okay? Degrees of freedom, I mean mesons and baryons in this case, okay? And the soft and hard would be going back, what is my energy? I'm studying low energies, and what is my hard scale, which will be the 1 GeV or the mass of the rho in this case, okay? Identify the symmetries, okay? And this is what now I'm coming to the symmetries of the QCD Lagrangian in the low energy regime, and investigate whether they are broken or not, because this, gives you an information on well, when I will discuss on the chiral symmetry, which is the symmetry in the low energy regime. You will see what it means there. And once you know this, you can start building your Lagrangian with all the terms that are consistent with those symmetries and with the symmetry breaking, okay? And finally, once you construct these Lagrangians, you can determine what each of these terms of the Lagrangian is going to contribute me or giving me an information on which are the most relevant contributions. Let's say you design or a scheme organized to distinguish the different contributions from the relevant from the non-relevant. Okay, you construct your expansion. This is blah 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 blah, and this is just an idea of what these effective field theories are and what they can do. So let's concentrate on the QCD Lagrangian and in the low energy regime and the chiral symmetry, okay? So this is a Lagrangian of QCD, okay? So you have here your quarks with different flavors, okay? So you have up, down, strange, charm, bottom, and top. I didn't put the color, okay? So also you have R, G, and B as the color, okay? Red, green, and blue. You have the kinetic term, right? This is this covariant derivative, was actually here. So it's the partial derivative. And then you have here the Gelman matrices, okay? And then this A mu are related with the gluon fields, okay? And then you have the, let's say the gluon strength tensor. So it will be like equivalent, right, to the QED1, except that you have this non-abelian structure, okay? You have this In the one that the electromagnetic, you only have these partial derivatives, right? These two terms here, but you don't have this one, okay? And this is what makes life complicated, in fact. So if you assume that the mass is small, okay, so I'm just thinking now about up and down. So I'm forgetting about strange. You will see that it's light, but right now I'm just concentrating on two flavors, up and down. And charm bottom and top are already too high, okay, are already lying here in this. So I'm just thinking about up and down right now. So in the limit, okay, of the small mass, so you have this Lagrangian, so you don't have this term here, okay? Well, it turns out this Lagrangian, okay, is invariant under these chiral rotations. So basically it means that there is some property, which is chirality, which the chirality in a few words is here. So it's the generalization of the helicity for particles without mass or highly energetic. So helicity, it means the projection of the spin into the momentum of the particle. And you can see here that this helicity for particles without mass is a good symmetry of the QCD. And this is what I wanted to show you a bit with this very fast. Okay, I'm giving you, as I said, a lot of information. And for those who have never worked on that, is maybe too much. But just that things sound, okay, familiar. So the idea is that you can construct some operators, okay? This is the left-handed operator, and this is the right-handed one, where you have the gamma 5, okay? And then those operators have certain certain relations, completeness, idempotent, orthogonal, okay? But the idea is that you can build the eigenstates of these operators, of this left-handed and right-handed. So these are the eigenstates of chirality for massless particles. So basically the idea is you can construct these eigenstates, which will be the quark with the left chirality and the quark with the right chirality, okay? And those are eigenstates of those operators, okay? This PL and PR. What I'm doing is basically I'm considering, as I say, this is the momentum, this is the spin. So this is the quarks with the right-handed chirality, and those which have the momentum and the spin opposite are the quarks with the left-handed chirality, okay? What I'm doing that because I want you to see that you can then construct the same QC de Lagrangian. I mean, this is that one, okay, where you had here UD. I'm telling you now that I can construct for each of U and D separately, you know, I can separate the right-handed and left-handed quarks, okay? So the fact that you can do that, okay, and this is invariant under these transformations, is giving you the appearance of what they're called new symmetries. And this is the SU2 left and SU2 right symmetry, or called as well chiral symmetry, okay? So basically, the idea is that the QC de Lagrangian without the mass term, okay, is invariant under global phase transformations that are given where the generators are these Pauli matrices, which means that the interaction between quarks and gluons is independent of the flavor and retains helicity. So quark with left chirality and right chirality don't talk to each other, okay? So I'm just trying to show you that there is a symmetry of this Lagrangian by building these operators here. So if there is a symmetry, okay, of the Lagrangian, it means that according to the Noether's theorem, if there is a continuous symmetry, this means that for every continuous symmetry in a physical system, we have a conserved quantity and vice versa. That means that if you have a symmetry in your Lagrangian, you have some conserved currents, okay? So basically, you can construct some, what they are called left-handed and right-handed conserved currents in this case. And these are the currents. So basically, they are conserved. That means the derivative, okay, are zero. And these are the ones, the left-handed chiral current and the right-handed, okay? So you have a symmetry, you have a current that is conserved, or you have a conserved charge as well. And actually, these currents you can also express. You can rewrite them as a sum and as a difference, because I'm introducing here what is this vector and axial currents. Okay, so in a way, I'm rewriting this left and right into vector and axial. So this is the sum and difference, and in this way, I can already discuss, talk about my original quarks. Okay, here I was separating between the right-handed and the left-handed. Now I'm going back, to talk about the up and down quarks without this left and right. But the idea is that this Lagrangian under isospin rotation, which is related with the vector part, is invariant. Okay. As I said, I mean, this is probably too fast for those who have never heard of that. In principle, it's also invariant and under this axial. Okay, there is this minus difference between these two currents. But this is for massless. Okay, this is for Lagrangian with no mass term. If you have a mass term, as the QCD Lagrangian has, this mass term of the quarks, you end up having a term which breaks this symmetry. Okay, so you have what is called explicit breaking of the symmetry, of the chiral symmetry, because this term here does not separate, it mixes left-handed and right-handed quarks. Okay, this is on one hand. So first of all, I just put you now how to break. I mean, what is the concept of breaking? Okay, so you can have symmetry breaking explicitly because you have terms in your QCD Lagrangian that breaks this, and this is only not broken if you consider very small masses, and this is the case we were assuming that the mass of the up and the down was too small. But if you don't, then you have this explicit breaking. And there's another concept. This is a bit more complicated to explain. I don't know if I will succeed. Is the spontaneous breaking of the symmetry. The spontaneous breaking of the symmetry, in a few words, means the symmetry is contained in your Lagrangian, in your Hamiltonian. But if you analyze the ground states, okay, the eigenstates of this Hamiltonian, your ground state, this does not. And this is for those who actually, I don't know if you have done something on chiral symmetry and the Mexican hat, So this is, as I will mention, the sigmas and pion fields, in fact, okay? So what I'm telling you here is that there is a symmetry which is not respected by the ground state. And this is actually observed already because the hadronic spectrum, okay, the states, the different states that you observed, does not contain parity doublets. So I was saying that you have a symmetry of the Lagrangian, which includes this vector part and this axial current part, okay? But now I'm telling you, yeah, the Hamiltonian does, but the spectrum experimentally, you don't see parity doublets, okay? And this is related with the breaking, spontaneous breaking of this axial vector current, okay? Because this axial vector current is related with the parity of the state, okay? Well, this is few words, okay? So just a few concepts that you probably, if you have never heard, you will probably forget, but if not, whenever you start reading about chiral symmetry or any effective theory, you will start thinking about the symmetries of the QCD Lagrangian, and then what it means breaking explicitly, what it means spontaneously breaking, and how actually this then correlates to the experiments, okay? And actually this also correlates to the experiment because this is the Goldstone theorem. I'm not doing any demonstrate, no, how it's called, new proof. I'm not proving it, okay? But when there is a spontaneous breaking of one of the symmetries, particles without mass appear. And in this case, the ground state, okay, or what you will associate, with these new particles are actually the pions, okay? So the breaking of the actual symmetry, the spontaneous breaking, is giving you what they are called the Goldstone bosons, which are massless almost massless particles. Okay, you know, pions have mass, a very small mass. And this is correlated with the small mass of the up and down quark because they are appearing because of this spontaneous broken symmetry, but there is also a small breaking explicitly that gives them mass. Okay. Okay. I mean, this is maybe, you know, a crash course in 3 slides, okay, on chiral symmetry. But what I want you to have in mind is that we want to build an effective theory, okay? We want to keep the symmetries of the Lagrangian, which is Lagrangian of QCD, at low energies. And at low energies, I have tried to show you there are some certain symmetries which are related with these rotations in the left and right handed, you know, chirality, which also translates into this vector and axial current, okay? And because of the symmetry you know, that we have to use this symmetry in order to build now our effective theory. An effective theory will take into account, for example, the first thing they will take into account will be pions, okay? These ghost bosons that appear. So I was very fast and I'm sorry about that, but really if you want a good, you know, reviews on that, I can recommend these 2 ones, which is reports of Anthony Peak and Volker Koch. This is actually pretty nice, this one, because it's really easy to follow it. But you know, recapitulating, I wanted to tell you, that we have tried, to construct our aim is to construct a Lagrangian, okay, that respect the QCD symmetries at low energies. So we identify the soft and the hard scales. This is the first thing we have to do. So the soft and the hard scales using our degrees of freedom, which are pions and nucleons. So, and our soft scales are the pion mass, the lower mass, and our hard scale is the rho mass. Then we have identified the relevant symmetries. In our case, we are talking low energy. We are talking about this chiral symmetry. And now we have to build up our effective Lagrangian compatible with the chiral symmetry, including all our degrees of freedom. So we have the pion-pion interaction, we have the pion-nucleon, and so forth. Okay, in this case, the first ones will be, 2 pions and nucleons. And of course, the idea is how we organize this. For example, if we look at pion-pion, there are different terms, okay, for the Lagrangian, different orders in the Lagrangian. And this is determined by our small parameter, okay? This is determined by this one, the separation between soft and hard. So in this way is how you build up an effective theory in case of in the low energies that should respect this chiral symmetry. Okay, this is just hints, okay, ideas. Probably everything's, for those who doesn't work, sound like weird at all, a lot, but this is just to introduce you what I'm interested actually, which is this in the last 10 minutes, just to show you that what people have been doing in baryon-baryon interaction, okay? So the idea was to build an effective theory that in order to have a systematic improvement on the theory by a power counting, so defining a small parameter, and implement 2 and also 3 body forces. I just was talking, all of the time about two nucleons going to 2 nucleons, but also people, think about 3 nucleons going to 3 nucleons, okay? But anyway, the idea here, if you're just thinking about 2 nucleons, okay, or 2 baryons, is to construct the potential, okay? Like in the meson exchange model, to construct a potential, but to know each of the terms, which is the most important one. And this is done by this power counting. And this power counting actually goes back to Weinberg, okay? And here you have a summary. Basically, these diagrams here corresponds to the first diagrams, which are most important. And this power counting is a bit more involved. I'm not how do you call it? Proving it to you. You have to believe me here that those diagrams here, which is called a contact term and the exchange of one boson, are the ones dominant in the description of the baryon-baryon interaction in using these chiral effective theories. The next two leading orders, so there will be the correction to those, are those coming here. So these are diagrams that are contact terms, but with derivatives. Okay, so you have then larger momentum. When you have a derivative of a field, you always have a momentum. So then you have become, this next two leading order are becoming more important as you increase your energy. And you have exchanges of two mesons. Okay, as you can see, different kinds of exchanges. So again, just a sentence to tell you that based on this effective theory idea that implements this chiral symmetry, you can construct the interactions in a systematic way, in the sense that the contributions of leading order should be more important than the next to leading order if we are in the low energy regime. As we increase energy, those start becoming important. And then you have probably to go and look at the next to leading order, okay? And then your life gets more and more complicated. These diagrams, as I said, are two baryon interactions. So you have a baryon entering here, a baryon entering here, a baryon exiting here, and a baryon exiting here. This baryon, it belongs to the octet, okay? So it's not only nucleons, now you have also Hybrons. And the exchanges are given by pseudoscalar mesons, okay? So this is, thanks to Weinberg, I'm not proving it to you, you have to believe me here. This is just to show you that these diagrams are most important than these ones. And actually the rule is given here, okay? So you have to count the number of incoming or outgoing baryons, the number of loops that involve mesons. You have to look at the number of vertices, and then in each of the vertices, you have to look at how many derivatives, how many of internal baryon vertex, and then you see that this is order 0 and this is the next order, okay? Again, here is just a bit more, complicated. And just to show you the shape, okay, of this contact term. The shape of this contact term is given here, okay? This is baryon-baryon, a leading order. This is the contact term. Contribution, the spin and the singlet and the triplet, and the triplet goes with the sigma sigma. It means the spin of the one baryon and the spin of the other one. So these are describing these diagrams: nucleon, lambda, nucleon and lambda going to lambda and nucleon, okay, because you have to conserve strangeness. Lambda nucleon going to sigma nucleon, and sigma nucleon going to sigma nucleon, okay? This is just to show you where the Lagrangian comes from, and those terms depend on the C3, C2, and C1s. I'm not giving you the details, but just that you know this is kind of the structure that you find in this contact term for these terms here. And the next to leading, and the leading order with this was the leading order of contact terms, okay, this term here. But those one here's are those appearing here that you already have in the one boson exchange model, but now here you are classifying in the spirit of these effective theories, okay? So you can compute in this the lambda nucleon by exchanging a eta and going to a lambda nucleon. Or you can compute the lambda nucleon and exchanging a kaon, okay? And then the other diagrams as well. Where those diagrams come from, again, with using Feynman rules, but looking at your Lagrangian with now, is the chiral effective Lagrangian involving baryons, this is this V's, mesons, which are included inside the derivative, the covariant derivative, through this, this function here, which depend on these U's, which these U's depend on the pseudoscalar matrix. This is this P, this is the pseudoscalar matrix. And actually, this is the kinetic terms. You can see the mass and the covariant, and then you here have couplings. But actually, the one Bose pseudoscalar exchanges come from these extra terms here, okay, that you know that come from here. And then the expression is the same that you already had in the one boson exchange model for this the interchange of a pseudoscalar, okay? The sigma 1q, sigma 2q, and the propagator, and then some couplings, okay? And then, well, this means which kind of reactions, the isospin, okay, of the B1, B2 going to B3, B4, depending on the values that you're looking at, okay? So in the second part, this is, I said, it is maybe too much for those who don't have any idea of effective field theories, but just that you know, the idea is to have a theory that contains the symmetries, the most important symmetries of the QCD Lagrangian at the range of energy that you are studying for low energy, which is the one that we are worried is chiral symmetry. And then if you know your symmetries, then you know how to build your Lagrangians using your degrees of freedom as mesons and baryons. And then you know also which is your parameter of expansion. And in the case of baryon, this is actually the contribution, the lowest order and the next to leading order contributions coming from this effective theory, okay? And just finalizing, I'm showing you the results for this effective theory, the chiral effective theory, at leading order and next to leading order. And how it compares with the cross sections that I showed you before. So, for example, I don't know, this one here again. So this is the band, because we can have corrections. I mentioned before, we can have a control on variation of the parameters in order to see how good or bad is this leading. Sorry, the leading order is the green one, which has the larger error, and the next to leading order is this one, the red one. Okay. I would expect for those who work here that the next to leading order will be closer to the leading order. Here there are some assumptions, because there are a leading order, usually in these cases, they are fitted to the data they have for some of the data, not all of them, otherwise it's not a prediction, right? And using symmetries, SU3 symmetries. And next to leading order, there are some assumptions in the coefficients, because we have more coefficients, more couplings, okay? And there's some of the assumptions are different, and that's why you don't see a convergence. For example, here it's difficult to see that one on top of each other as you would expect, okay? But anyway, just to show you the power, okay, of going through effective field theories, and in particular through this chiral effective field theory. I think I have this also for the Hyperon, for the cascade nucleon. Here there is only actually used here one data, and it's an upper bound. It's not even, okay, it's an upper bound. So basically, you see the results coming from leading order and next to leading order, which again, I didn't show the color here, but the leading order is the green, and the next to leading order is these ones here, okay? So again, this is the problem of conversion, and this is because there are some parameters which are fixed differently, okay? But anyway, this is because the lack of information, because there is always a bit of feedback, you know, between some data and the couplings of the theory. And again, an example of the data on Spectroscopy, okay, on this particular cross-section cascade nucleon, okay. Okay, so I think I will stop here, because Hypernuclei I can talk all the day. I mean, there are 3 or 4 slides unless you want it, but it's already 4. So I don't know if people are already, I guess, already exhausted. So.
Well, as you want, I would stop here actually, because maybe there are some questions.
Yes, definitely.
From the audience.
Yes. So it was a bit hard. I know. Sorry.
No, it's perfectly okay, of course. Actually, it's very interesting, and I have also many curiosities, but okay, we have time also in the next days to ask. It's not.
Sure.
So.
I mean, I have to confess, I'm a user of these effective theories, okay? So I know how they look like, I know how they work, I never built them, okay? So anyway, you can ask me if I don't know, I can point you to how they actually build some of these things, okay?
Okay, the students first.
Yeah, can I ask a question?
Yes, Matteo, yeah.
Okay, thank you. First of all, thank you for your very nice lecture. I would like to ask more details about the error bands you showed in the last plots.
Yeah, they are very different. Wait, do you see still my slide or not anymore?
No,
not really.
No, not anymore. Okay, let me now again I share because I share. Okay, here. Okay, I don't put it in full screen. I just put it like that. Yeah, those arrow bands. Okay, right.
Yeah.
I mean, those arrow bands, for example, the leading order, I always forget, is this green one,
yeah.
I think. We have some couplings. We have these couplings. Okay, the leading order will be those couplings here, which are actually 6 independent low energy coefficients, plus some couplings, which also this DNF, which also have some errors, which are reflected here, and also weak decay. So there are some couplings that you know experimentally, some others that you fix by symmetries. So there is this error bar coming from the variation of this between some reasonable ranges. Okay, so this is where the bars come from. Okay, you follow?
Okay,
That's your question.
So you take the upper value of a set of
yes,
couplings
exactly.
and the lower value. Okay, yes. But this is also related to for example the scales. They are the soft scales. For example, if you take the 1/2 the mass of the pion, or 2 times the mass of the pion.
I would say not. Okay, but since I didn't build it up, I would say no. I think it's related to these couplings. Okay, the variation on the couplings. Okay.
Okay, thank you.
I have a little comment. As theorist, I am impressed by the data, by this spectroscopy, which is absolutely impressive. The fact that in an experiment which is performed at the scale of the tera-electron volt, you are able to extract information on scattering which takes place at a relative energy of a few hundred MeV. It's magic. I mean, and not only that, but I expect that in the next runs with high luminosity LHC, this data, this information will be more and more precise. So it's really very, very relevant for the field, also for astrophysics, you will tell probably.
Yes, I mean, yes, the point is that we, up to this moment, the data was very little. So anything really constraining the interaction, then it propagates into a medium calculation, okay, in a neutron star. So I'm a medium person. So any improvement there, really reducing those bands even, because of the data, will give you more constraints on what's happening in any place in neutron stars, for example. Okay, we also have to be careful, okay? Neutron stars are some objects really high in density, okay? So we also have to be careful, what we say, okay?
Okay. Other comments, questions?
Sorry. And are there other experiments that are supposed to shed light also?
Yeah. Well, for example, in hypernuclei that I was to mention, but I didn't show. Actually, I didn't put any slide. There is there is a GSI. There was a program in Germany for hypernuclei, but in Japan, JPARC. It's really focusing on these hypernuclei, okay? And there is also, I think, programs on improving the experimental data in different, I don't know the details right now, I can dig it up, but in JPARC, especially on strangeness and how to get better data, okay? But in particular in hypernuclei. So maybe if there is an experimentalist working on that, can give more info, but there is. So, and there are lots of people working on in Italy as well. So,
Okay. Thank you very much once more. Very interesting.
Thank you, Matteo. So if there are no other urgent questions, I would stop here. Thank again to Laura, of course, and we will see her again on Monday afternoon.